Hello and welcome back to my review of my 6502 ASM solutions for Advent of Code 2023. We're up to day 3 and today things get a little interesting. So let's get started. Let's look at the problem. So we are wanting to take a gondola today and it appears the engine is missing a part. But if we add up all the part numbers, we should be able to work out what part is missing. So what we do is that we get an input that looks like this. Okay, it has numbers, it has periods, which are effectively empty spaces, they do not count as symbols, and it has symbols, right? So for part 1, any number that's adjacent to a symbol, even diagonally, is a part number and we should include it in our sum. So in the schematic there are two numbers that are not part numbers because they're not adjacent to a symbol. Those ones here, this one is not, there are no numbers around it, symbols around it, and 58, this one here is not. Every other one is a number because it's adjacent to a symbol. Alright, so again, today I'm doing the two parts together. I think originally I did finish part 1 on the day itself, but it took me like another 2 or 3 days to complete part 2. So I did actually do them separately, but then I put them together into a single file as I wrote the solution. So what else do we have here? We'll look at part 2 as well. So once we've finished that, it turns out that there are gears. Each asterisk is a potential gear. If it's adjacent to exactly 2 part numbers, it is a gear, and you multiply the two numbers together to get a gear ratio. So if we look at our input again, you can see, well, there's this asterisk here, there is a number adjacent here and here, so it is a gear. This one here only has one number here, so it is not a gear. This one here has a number here and down here, so it is a gear. So we now have to, for part 2, we have to figure out which asterisks are gears and then multiply the two numbers together. So that's kind of annoying. We end up with very big numbers as well, so that's also fun. So how did I solve this one? Let's have a look at the code, shall we? Let's have a look at the code. Let's get rid of this for now. Alright, so first things first, something new. Program. So what turns out that on the Famicom, the NES, you have 2 kilobytes of system memory. But there is an address space starting at 6000 going to 7FFF that is addressable on the cartridge, but it is not the program ROM. That starts at 8000. So what you can do is that you can have you can put another chip in there, like memory or a mapper chip, and you can make it addressable on these 6000 to 7000 address ranges. So what I've got on my cartridge is that address range is effectively mapped as RAM. My cartridge will treat it as random access memory. I can store data into it, I can load data from it. So what I'm doing in this program is that I'm clearing out half of that. I think I have 8 kilobytes. So I'm clearing out 4 kilobytes and making 4 kilobytes of it ready for my program. So do that first, right? This one here, buffer for numbers. Okay, we're using basically the same thing as last time. 31 is the length of the number, the offset 32 to 34 is the number itself in decimal. So 32 would be the first digit I come across, 33 is the second digit, 34 is the third digit, 35 is a check to see if I'm adjacent to a asterisk, 36, 37 is the address, the memory address on the input of that asterisk if I have one. And 30 is telling me if it's adjacent to a symbol, right? It's just a flag. So then I set up a pointer. This is my insertion pointer for adding stuff to my gear table, potential gear table. Set that up as 6000 and 00. So 6000 in the high byte OF, 00 in the low byte OE. We have, what we've got here, the size of my input again. I'm storing that still. And here I'm doing something a little interesting. So I load the input into 3 different addresses. The input pointer address, right? The low byte into 10, 12, and 14, the high byte into 11, 13, and 15. So what I'm going to do, I have this thing called address of trailing lookup and address of leading lookup, right? What I'm doing, and I'll bring back the browser so we can look at this. What I'm doing is that my program will effectively search through like this. It will go along checking each byte. But I'm also checking the bytes above and below. So when I check this byte here, I also have an address pointing at this byte and an address pointing at this byte, right? The addresses that are directly above and below. So this is why in my input here I have this compare test OC input 8E. That's the length of the lines in the input, right? So I get to the line, the addresses above and the address directly below, right? So I've got a trailing lookup address and a leading lookup address in these 20 and 12, 13, 14, 15. And so I have to, after setting up the addresses, firstly I subtract the offset for the trailing address here, and then I add the offset for the leading lookup here. Okay. And I think that's fine. I think we're fine. Yeah. Alright. Okay. I'm not sure. I'm just going to say I'm not sure exactly why I have OC for this one and OA for this one. Ignore it. I'm sure it's fine. I'm sure it works. Okay. So we set up those addresses. So we're effectively going along the same as before. So what am I doing? Enter the input address, load 19. I store it into, where am I? Load 11. Arrow carry, clear thing, arrow carry 19. Restore it into 17. I'm setting up the end. I'm setting up the end addresses for the input as well. Load 10. And carry 18 and store it into 16. Yeah, I think I'm right. So what I need to, in here in 16 and 17, I'm storing the final address, the final memory address of the input block, and that is needed for my bounds checking, because when I'm checking the when I'm loading, as I'm going along, when I check this address, the trailing address is outside the input, right? While the leading address is inside. Once I get to the final line, the leading address will be outside the input. So I need to have where the input ends as a bounds check for that leading input. So I'm not checking sort of outside the memory range. I could get anything could be out there. Okay, so once I've got those ranges checked for the bounds, the input bounds, we set up our counters. I've got I'm not even sure if I use 9, but I've got it here anyway. This text here, you can see it's carried over from the last day. That's all right. We go into our loop. So my loop here, we check if the byte is 0. If it's a 0, we've finished a line. We might need to save a number, right? If we have this input here, down the right side, it's all got dots, all got periods. So you'd always have a symbol that would end a line, but on the actual input, that's not the case. You could just have a number going right up to the edge, and that got me at least once on the input. So yeah, you have to actually check. I actually have to check if I've hit the end of the line. If I have, then I might have to do something, right? If it is a 0, 0, I do deal symbol, right? I jump to deal symbol. If it's below 30, a symbol below the decimal 0. So here, actually, let's have a look at the ASCII table. So this is the ASCII table. You can't see my cursor, can you? Let's change this for a second so we can capture the cursor. Okay, here we go. So here's the ASCII table. You can see the hexadecimal column down here. We've got the ones in the character, digits in the characters going from 30 to 39. Now the symbols, right? It could be a plus sign, it could be an asterisk, it could be an ampersand or a dollar sign or anything up here, which would be less than 30. And I think question mark is possible, @ sign might be possible. I don't know, anything up here greater than 3A. Well, 3A or upwards, right? So I need to check both of those to those ranges to see if it's a symbol, if the character I just loaded is a symbol, right? So I think we're good there. I think we can get rid of the browser now. Let's get rid of that. Okay. So here I'm checking if the character I just loaded is a symbol. If it is, we will jump to deal symbol. If it's not, then it's a number. So we will store it into this is here again, same thing we're doing yesterday. We load our offset from 31, we AND the value that we just loaded with F to get the hexadecimal value of the character. We load, loading A with, we're storing A, sorry, storing A into 32 with the offset of Y, with the offset that was in 31, increment Y, and we store that into 31, right? And this is where we get a little bit special. We're backing up X and Y, and we're going to this, jumping to this LR ADJ, which is left, right, not adjust. It's a left, right check for a symbol, left, right symbol check, effectively. So let's get the browser again for a second, actually. So I load, let's say I've loaded this number here, right? I want to check if there's a symbol here. I want to check if there's a symbol here. Then I want to check if there's a symbol above it or a symbol below it. And that's what I'm doing in this area here with these jumps. So let's go, let's have a look. LR ADJ, there we are. Okay. So, right, we work out the address that we're at. So I load a 11, I store into 3B. I've got a mess, an absolute mess here, because I need, well, for simplicity's sake, I want to use the actual address that I'm at, not the offset, not using the offset, because in the normal loop I have the address of the start of the input, and I use Y as an offset, and then I'll increment the high byte as the offset rolls over, carries over. So what I want to do is I just want the actual full-on address of this byte, right? I want to add the offset to the address that I'm loading, used, and store that. So I take that high byte, and I store it into 3B. And I take the low byte and I store it into 3A. Then I add the offset, that Y value, to 3A, the low byte. And if it's if it overflows, if it carries over, then I increment the high byte. But now I also want to go back one step, because I want to look at the character, this character here, right? The one before the one I'm on. So I decrement the low byte, and now I have to check if we've just rolled back to FF. And if we have rolled back to FF, then I need to decrement the high byte. What a mess. Right? And so, but now I'm ready to check the left side. We jump to read 3, which is going to read 3 bytes. It's going to read those 3 bytes, and it's going to look for any characters. Right? So let's go down to that read 3, shall we? Well, where's my read 3? Here we are. So firstly, the bounds check. This is where that bounds check comes in. Right? I'm loading that 3B value, checking if it's outside the bounds of the, if it's less than the starting input. Right? Is it less than the start of the input? Right? I'm doing that check here. If it's not less than the start of the input, then we go to the upper bounds. We check the upper bounds, which is in 1617. Right? And I compare that, the address to that value, see if we're within that address input. And if that works, then we branch to this run RT, which was a run check. I load Y with 2, because I'm going to load, I need an offset of 2, 0, 1, 2 to load those 3 characters. We jump to sim check, which I think is right below it, yes. So I load, value the offset of Y, which starts off as 0, right? We load that that value there. Here's my end of line rare case, right? If it's the very first one here, then I'll have an end of line over here for the first byte, that first check, and would skip it, right? Next we check to see if it's a period. If it's a period, right, in this case, looking at 3, that's a period, we ignore it, right? We ignore it, we skip, it's done. Next we check if it's an asterisk, right, which is hex 2A. Look in the table, 2A asterisk, yeah. Right. If it's not an asterisk, we branch to no gear, which is like down here somewhere, right? But if it is an asterisk, I load, if it is an asterisk, first I have to check, have we already found an asterisk, right? I think I may have checked this, the input, you never have more than one asterisk next to one number. So I'm not even sure if you have more than one symbol next to a number, but I think you never have more than one asterisk next to a number. So if I've already seen an asterisk next to this number, right, this number I'm loading, say this number here, if I've already seen the asterisk, then it will have been flagged and we can ignore this, right? So if 35 is not equal to 0, then we branch, we're done. But if it is equal to 0, we store 1 into 30, we store 1 into 35, which means we won't hit this gear again, we won't store it again, and then we save this address with our offset of Y that we're using up here. Will be 0, either 0, 1 or 2, adding that on into 3637, right? And we have to check if it overflows as well, right? We add on the offset of Y to 3A, and if the carry is set, then we have to increment 37 again, and then we store it 3A into, or that value from 3A into 36. But if it isn't a gear, if it isn't an asterisk, right, then we check if it's a symbol. Right? If it's a number, like say we hit, it probably would have been faster if I checked if it was a number rather than a symbol. But anyway, if it's a number, we ignore it. If it's anything that's not a number, not a period, not a asterisk, then we will store 1, load 1, and we'll store it into 30. Right? And the same thing over here. Load 1 into 30. And then we're done. Right? So it will do that 3 times on these 3. 1, 2, 3. So it does get itself. That's okay. Then the second one it loads will be this one down here. Second check. Up, down, adjacent. ADJ adjacent. Right. So we load the trailing address. Right. We do the whole adding the offsets to it again and adjusting it. Right. And then we jump to the read 3, the same as before. So the trailing address, we'll check these 3 up here. And then it will load the leading address, do the whole adding the offset stuff again, jump to add 3, and it'll load these 3 values and check them. Right? And then it will return. It will return finally back up here. Right? And then it'll restore the X's and Y's. Do that all the time. And then it will jump to increment the memory. Right? To go down here, increment the Y. If Y rolls over, it will increment 11, 13, and 15. And here's our check for the end of the input. Right? So finally we get to deal symbol. Right? So if we've the value that was in, well, the value that we loaded in our loop, this one here, if the value we loaded here was a symbol, right, we check what's in 31. If 31 is 0, you know, we've loaded no number. There's no number in there at all. Right? And so we just increment, right? We increment the memory, and we just keep going. If 30 is 0, right, then we've finished a number, right? We've read a number in, but it wasn't adjacent to a symbol. So we need to clear the number, right? And where was clear num? Clear num was down here. Yep. And you clear the number, back up Y. And then we zero out from 30 to 39 in the memory space. Restore the Y, and then we increment the memory. Right. And if those didn't happen, then we jump to add num. Right. And then once add num is finished, we'll go and clear the memory again. We'll clear the number out of the memory again. Right. So our next stop is add num. Let's go add num. We're getting there. We're getting there. It's been 20 minutes, I think, but we're getting there. All right. So we've loaded a number, and it's adjacent to a symbol. Right? It's adjacent to a symbol. So what are we doing? We're backing up X and Y. We always back up X and Y. we load 35, right? Is it 0? If it is 0, then the number was adjacent to a symbol, and the symbol was not a potential gear, right? So we just add it to our part 1 total. We jump to do addition. We'll get there in a minute, I think. If it was 30, if the value of 35 was 1, was not 0, it was 1, then it could be, right, this value could be the second number that was adjacent to this asterisk. Now, I think this is, I may have mentioned this before, but I checked the input to be sure, and there are no cases of an asterisk that had more than 2 numbers next to it, right? There were no asterisks that were adjacent to 3 or more numbers. So I can get away with just this check. It says in this input, right? Let's make sure we got it down here. It says in this input adjacent to exactly 2 part numbers, but it looked like in the input there was just 1 or 2. A case of either 1 or 2. Right? So I can get away with a simple check like this. So what do we do? If it's JSR, right, we jump to this is gear check. If it's next to a symbol, next to an asterisk, we jump to the is gear check. Depending on the output depending on the value of the X register, when we come back from that check, we'll decide if we do addition, we jump to do addition, or if we just keep going down here, right? So let's just keep going first. We'll say it comes back X is 0, so it's not equal. We keep looking down this, right? So what do? We load Y with 1, then we load the top byte of the address of the asterisk that was next to this number, and we store it into this address here, which is the pointer address for our program. So it starts off 6000, right? So the first byte, 6000, yeah. So it will store the top byte into the address 6000. No, 6001. It'll store the top byte into 6001. It'll decrement Y, see if we are, compare Y to FF, see if we're finished, and then it will load the value of 36 and store it into the address 6000, effectively, right? Then we'll load the value of 31 that's in there, right? Which is the length of our input, either 1, 2, or 3, right? Whether the number is 1 character in length, 2 digits in length, or 3 digits in length. We'll decrement it once. So basically I'll make it into an offset. We'll load Y here, and it'll increment that twice. Right, so if it was 3, it'll make it now 5. And then we load A with that value 31 with the X. Right, so it will load the last digit in the input of the number, the final, like the ones digit of the number, and it will store it into Y here. It'll store it into, well, this memory address here, right? And then we decrement both of them we compare it to 01, and we loop through it. So this is storing the number. This is storing this number we found next to a potential gear, an asterisk, into this table in memory. And this table in memory has 6 bytes here. It's going to look 6 bytes long. Now I think I stored the length of the number as well at some point. Let's see. I'm not sure. I must be storing the length of it somewhere. I'm about to get very confused as to how I saved the length of this number that were just loaded out of the input into the table that's in program. And that's because the way I did it was very confusing. But I've worked out now, so I'm going to explain it before all the confusion begins. So, we have the length of the number stored in 31, which I'm loading out of there and storing into X. And I also load it and store into Y, which I add 2 and increment twice. And this is for the offset into the table that's on program, right? I add 2 to it, so it will be placed after the memory address of the potential gear, right? So, and I subtract 1 because the offset, the length of the number, if the number is 3 digits in length, you want an offset, a maximum offset of 2, 0, 1, 2 for the number itself, right? So I have this little loop here. I'm loading from 32, which is the first digit, 33 would be the second digit, 34 is the third digit, with the offset of X, right? If it's a 3-digit number, that would be plus 2, so it would load from 34, and then it stores that into Y, which would be 3 plus 2 with offset of 5, right? Then decrement X, decrement Y, and now I'm comparing Y to 1 to see if the end of the loop, if I reach the end of the loop, right? So go back again, the decremented, so 32, we'll pretend it's a 3-digit number with an offset of 1, right? So it loads from 33. We store it into here, into the table with an offset of 4, right? Then we decrement X and Y, right? And then offset of 4, yeah. And then we loop again, right? Then so Y would now be 3, right? So we loop again. Now that this will be 0, right? The offset will be 0 on X. So we'll load from 32. We store it into here with an offset of 3. Decrement X, decrement Y. Y is now 2. So we haven't finished this loop yet. But X is already, well, X is gone, X is rolled over to FF, right? So we go through the loop one more time. Now, you would think, now that offset is FF, right, I'd load, this function would load from memory address 131, because 32 plus 255 would be 131. But that's not what happens. Okay? See, what happens, what's going on here, right, is that because I'm using an area of memory called the 0 page, it only uses 8-bit addresses, 8-bit addressing. And that's also why I have to use X here for the offset and not Y, which I'm using down here. Right? So, because it's only an 8-bit address, it wraps around the 0 page. It wraps around the first 255 or 56 bytes of memory. So this offset of 255 is effectively -1. So right now, loading from the 32 with an offset of -1, it loads the address 31 and stores that with an offset of 2. Right, so just past the memory address, decrement X again, decrement Y is now 1, breaks out. So, but why? Why did I do that? That's the big question. Because I could have easily just done this. Oh, there we go. And it should be exactly the same. It should work exactly the same. But I didn't. Why I didn't, I don't know. But that's why I was so confused. Alright, let's get back to the video. 32 X. Y into there. Interesting. I'm not seeing where I actually store the length of the input into wait a second. I think I'm being a little bit tricky here. And I'm effectively storing the what? Surely I'm not. Wait. No, that can't be it. So I store A, which is going to be that the X, 32X. Yeah, I'm not really sure how. Somehow I'm storing the length of my number into this as well. So what I'm doing here, and then I update the table, the input table pointer. That was an E, address E and F. I add 6 to it. And so the next number that I come across that's next to a gear will be input into the table further along. I'll show that when I run the solution later. I'll show the memory of that going along. So effectively what I'm doing, right, let's just say we've got our address at 6,000. Oh, let's put on over here. We've got this address 6,000, so at 6,000, right? And I'm storing the low byte of an asterisk and the high byte of the asterisk, and I'm fairly sure somehow I'm also storing the length of the number that I've got in here, and then the hundreds, tens, ones, right? And then the next one, and then I increment it so that the next will start at 6, right? So the low byte's at 0, 1, 2, 3, 4, 5, and then the next one. So I've effectively made a table in memory that's 6 bytes long, and every 6 bytes is going to be an entry into this table. That's potentially the location of a gear. The memory location and the location in memory, in the input memory, where that gear exists, and the number that's associated with it, right? So let's get rid of those, and then once this is finished, then it just falls through into do addition. So whether we branched here from up the top here or not, we end up just falling through into do addition, right? So let's have a look at the do addition, shall we? So I load the counter, we're using counter 1 when we're doing addition, and we jump to numcalc. Let's have a look at I should have put a thing on that. Here we are, numcalc. So we back up x and y to the stack this time. So this time I'm basically doing the same as yesterday, with one caveat. This time I'm not converting the decimal representation of the number that's sitting in memory from 32, 33, 34 to hexadecimal. What I'm doing is I'm just adding those digit values into the ones, tens, and hundreds columns of my counter. Right. So I load that x offset, load into x 31, the value of 31, I decrement it once. Right. So I load that value from well, y is my pointer condition, pointer. The offset position in the counter I'm pointing at, which will be the ones column here, using 7. We load the first number from, we load the last number. Okay, we load the last number from my input that I've collected, and we add it into the ones column. We check if it overflows. If it doesn't, then we go straight down here to skip tens. If it does overflow, we subtract 10 and we increment the tens. And incrementing the tens, we'll increment the hundreds if it needs to, and we'll increment the thousands if it needs to, and it'll just go all the way up. And then we fall into tens anyway. If x is now 0, we are done, we just go to skip thousands. If it isn't, then we decrement it once more. We point to the 6. So I probably could have, yeah. Probably best anyway if I load y anyway from it. Load y, right, we take the next value out, we add it in, and then the same for the hundreds column, right? So instead of doing that conversion into into hexadecimal representation, and then subtracting out small amounts from it like I was doing the day before, I'm adding it into each column, which is quite a bit faster. Quite a bit faster. Still not the best way of doing it, probably, but actually no, I think it might be one of the best ways I could do it. But I think I could probably speed up some of this checks if I really tried. Anyway, skip that thousands, and then we return. We RTS back once we've finished adding the number to the counter. Right. So there's one more thing we really have to look at, and that's this is gear check. Right, which is just down here. Here we are, is gear check. So what are we doing in this is gear check? Well, if we find a number, let's have a look at the input again, right? So the first time we find this number here, we check if it's next to a gear, right? Well, it's clearly not going to be the second number next to a gear, right? And I haven't even added it because we see that the add this check, where is it? Here we are, right? We do this check here at this point before I would add it to the table, to this table that's in 6000, right? In fact, we will skip that entirely. That's what this value here is for, this check here is for, right? So we'll say like the first time you come across a number that's next to an asterisk, we'll come into this is gear check, and it's going to go looking to see, is there a matching memory address for that asterisk you found already in the table. Right, so we pull up this set up the table search pointer. So we're starting at the start, 6000 and 00, starting at 6000. We're going to loop, we're going to load our Y, that's our offset of course, and we're going to loop through our table. Now this is something I made a mistake, I think, with. I should have had some kind of value that was easily identifiable for the beginning of each value in the table. Because I use memory addresses, you can have a memory address that has a low byte of 00. And so I couldn't use a check for 00 here. I've cut it out, but I haven't cut out the comment to look for the end of the potential gear table. Because, and I think this happened on my input, if you have a gear which aligns onto a memory address that ends in 00, you would end your search before you actually got to the end of the table, and so you wouldn't find all the gears. So that was a bug that probably, I don't know how long it took me to find. Maybe it took me a couple of days to find. May have just been one day. Anyway, so we're looping through this table, right? We're going to store this Y, we're going to back up this Y, this offset. We load the value, the first 2 bytes that we've come across are going to be the memory address, the address of a potential gear, right, from the table. The memory address from the input. So we load the value that's in OD, which is the top byte. We store that into 4D. We transfer Y to A, and we store that into 4C, which is going to be our low byte. This time it's aligned with 00. The offset is aligned with 00, so we don't have to do any addition. Right? We don't have to do any addition and any fail carry checks to see if we have to increment the high byte. It's aligned with 00. We don't have to do that. It's fine. Then we load Y with 00 again. Here we go. We're loading out the number, I think. Let's see. 4C. We're checking. This is here. We're checking to see if the address of the gear, the potential gear, the address of the potential gear we loaded from the table matches the address of the potential gear of the number that we have just read from the input. So say, right, we've just read 35 from the input. We go through our table, we find this gear associated with this number in the table, and so we check if the gear that we found when we were looking at this number, right, the address of it matches the address of the gear we found when we found this number, right, if that's the same. So, we're checking the low byte, see if it matches, and the high byte, so see if it matches. If it's no match, then we jump out. If it has matched, we have a match. It is definitely a gear. We jump into multi-gear. When we finish that multi-gear, we load 1 into X here. X would otherwise be 0. We restore the Y and we jump to finish add, which down here would be going back, right? We have that check. If it's not a match, then we add 6. We load A4E, which was our offset beforehand, or the Y offset beforehand, which we backed up over here, right? We backed up the Y offset, so we load that back. We add 6 to it because with every 6, if that rolls over, then we increment D, right? And here, I'm effectively just checking to see if we have passed, on the high byte side, if we have passed the input bytes, the input address, the high byte of the input pointer for the table. And that's how we break out, right? So every time I will check more area than I've actually input, but it doesn't go too far. So this is inefficient, but it works, right? If we haven't overflowed, then we go back to the start of the table to try again, to see if there's another byte, another potential gear that would match. So let's see. So we've made it to multi-gear. We've got right, we've loaded this number, we've looked through our table, we've found this potential gear that is associated with this number, right? So we're going to jump into the multi-gear part, which is right down here. Right, we're going to jump straight to number to hex. We're actually going to do a number to hex conversion, right? Let's do it then. So where are we? Let's go num to hex. There we are. What was that? No. Back up X and Y. Always back up X and Y. We clear out the what we're going to have is the top byte and the bottom byte. 46 and 45, the bottom byte. Right, we load Y with O2. Now we're loading the length of our number, which we've got in 4C apparently. And now I'm like trying to remember, when did I put a number into 4C? 4C. I think that is a memory address that I have back up here. Where was it? Over here. Oh, +2. Right. We loaded this out of the table, Loaded D. Yep. 4D and 4C holds the address of the asterisk. That was in the table. Right. So the next one must have been the length of, with an offset of 2, must have been the length of it. There we are, we're down here. Right, the length. I'm still trying to think of how was I storing the length of the number in that table. I didn't see it. Anyway, that's fine. So take out the length of it, restore it to 4A. We clear our carry, we add 2 to that, and we transfer that into Y to get our real big old offset, a full offset, right? So that's the adding 2 gets us past the memory address that's in that pointer, right? The first 2 bytes of the memory address, and then we have the address, the length, and then 3 bytes that are, or up to 3 bytes that are the number. So adding 2 puts us past the memory address right? Alright, so then we load the first number. Right, we're loading the first number. We compare x. X should start off at 0, so it starts off at 0. If x is 1, then we branch into m10, which multiply by 10. If x is 2, we branch into multiply by 100. Otherwise, we just store it into 45, which is the bottom byte. Right, we're using 2 bytes because we're up to 16-bit numbers here. That's fine. And the bottom byte, we jump to next digit, which is all the way down here. We increment x, we decrement y, we compare y to O2. If it's O2, we're finished, we break out and we finish off. Otherwise, you go back up. Right? So the second time through, we are multiplying, like it's the second digit, we're multiplying by 10. Easy. Easy way to multiply by 10. You take your number, you shift it left 1, that multiplies it by 2. You store that multiple of 2 somewhere. We store it into 4b. Then you shift that value across 2 more times. Multiplies it by 4, then multiplies it by 8. Well, multiplies by 4 and then multiplies it by 2 again, right? Multiplies it by 2 and then 2 and 2. So you get a multiple of 8. Then you add that value you stored, the multiple of 2, to the multiple of 8. And now you have a multiple of 10. And we store that, we add it to 45, right? Because the maximum value in 45 right now would be 9. The maximum value of the A register would be 9 times 10, so 90. We're still an 8-bit number, we're fine, we can just store it straight into 45, doesn't matter. No problems. And then we jump to next D. If I've made it to the third time through this loop, x will be 2. We'll jump to M100. Now we have to multiply by 100. We're doing something very similar. Okay, it starts off the same. We're multiplying by 10. Right, at this point, right, we've multiplied by 10. We shift it across one more time. We've multiplied it by 20. Right, we are still within the bounds of an 8-bit number, so we store that into 4b. We're fine. We shift it across one more time. Now we have to start rolling the carry flag, the carry bit, into 46, our high byte. Right, because we could have a number that's bigger than 8 bits. So this one here, effectively multiplied by 40. We shift it one more time. And we roll into 46 again. We're effectively multiplied by 80. Right? We clear our carry. The value that's in 4b was multiplied by 20. Right? So we add that. We add that to our A register, which is effectively the bottom byte of the bottom 8 bits of our 16-bit multiple of 80 that we have. And if we overflow, we increment 46 one more time, and then we add the value of 45, which is our, the bottom byte of our 16 bits, to the A register again. We check if we overflow again. We have to check if we overflow again. If we do, we increment 46, and then we store that bottom byte into 45. And there we've done a multiple by 100. Right, multiplied by 100. So we will be done now. The value in 45 is the low 5 bytes of low 5 bits of a 16-bit number. The value in 46 are the top 8 bits of the 16-bit number, right? And we're done. We RTS. We go back. Where are we going back to? What was it? I can't remember what it was now. Can't remember what section. Let's go back. We'll find it. Multi-gear. Here we are, multi-gear. Right, we've done the number to hex. 45, 46 is our multiple. Right. We select counter 2. We are using we're using the number that we have in dy and dx, which was the first number associated with the gear, right? It's this number here is now going to be our loop, the number of times we're going to loop adding the second value, this one, to the counter. Right. So loop m, this is our loop multiple. We're going to do numCalc, which is exactly the same as before, except we're using counter 2. Right? And every time we numCalc, we decrement y. If it's not 0, we go back to start loop m. If it is 0, we decrement x. If x is not negative, then we go back up here. But if we have hit a negative, right, if it is ff and y is 0, then we're finished and we RTS. Right. We would RTS all the way back up to multi-gear. X would come out, I think it's from multi-gear. Now x is a negative there, right? Alright. Of course, right? We come out in multi-gear, we load x with 1. We restore y. We jump to this fin add, which would go back to, where are we going back to? Where are we going back to? Here. We'd end up back over here. Right. We would then, coming out of that check and multiplying for part 2, we would add part 1. Right. Then we end up getting down to the bottom, jumping to numCalc, ending numCalc would take us back to, where would it take us back to? I think it takes us back all the way back up here to add num. We'll clean the num out and we'll increment the memory. And that is everything. Right? So to break it down again, what I'm doing is that I'm going through the input like this. If I find a number, any number, we check the addresses below, the 3 below and the 3 above. Let's take this number here for example. When I find a number, I check the 3 above, the 3 below, and these 3 here for a symbol. Once I hit any other symbol, I check if there's a number, right? If I have a number saved, say this number saved. If it was next to a gear or next to an apostrophe, we save it. No, if it was next to apostrophe, we check if that apostrophe has been seen before. If it has, then we multiply the number that was associated with it by that number and put it into part 2. If it hasn't, then we save that potential gear and the number associated with it into a table and we add part 1. And either way we add part 1 to it, and we do that until we get to the end of the table. So all of that was done. Let's have a look at it running, shall we? So our first result is 500,000. The second result is 72 million. So I've had to change messing a little bit. I've got a few more digits, right? So I'm using background for all of the text on the screen now, using background rather than sprites, because you need to have, if you have more than 8 sprites in a row, you get problems. And I've got, actually, I've got 8 exactly, so I might not be using backgrounds yet. That's coming anyway. Okay, let's get this started. Let's run this first. So here we go. You can see it's kind of, like the part 2 is coming up constantly. Part 1 goes a little bit slower. Right. Part 2 is really the slow point. If you watch really carefully, you might actually see letters appear and they disappear as it actually it actually cleans up the letters when it rolls over. Man, this takes quite a while, doesn't it? It is mostly that loop doing the multiplication that is taking all the time in this. As you can see, part 1, it's sort of starting and stopping, stopping, starting, stop. And we've hit the end. And how's our number looking? Let's see, we've got that number there. That's looking pretty good. Right? 725, what was it? 72553319. Yep. We're good. And the first number, 507214. Yep, we're good. Okay. Let's have a little look at the memory, shall we? I think I have to get rid of the browser here. Do I? Oh. I thought that window capture was there. Where is this? I can't see anymore. Where is it? Where is it? Missing. Thought I had it. Thought I had that one ready. Oh well, let's find. Right. Let's get rid of that. Let's get a new one into here. Here we are. Okay. So let's have a look at, let's make this a bit bigger as well. What's going on here? So you can see I've got this open. We've got memory address. We're starting at 6,000. You can see all of this in here already, right? You can see I've got an address here. It's saying it's 3 in length. I really should find out where that is. Right. So effectively, right, at this memory address, 8906, there is a asterisk, and it's a 3-digit number, so it should be 489 is effectively the number that was there. Then at 8927, there's another one, and it's next to a number that's 152. Right. 8946, there's another one. It's another 3-digit number. 180. 8955C, another 3-digit number. 147. 8982, another 3-digit number. I'm sure there must be some 2-digit number somewhere. 3. Maybe there's no 3-digit numbers. Oh, doesn't matter. I'm sure we'll find. Yeah. So let's run this again and let's watch it populate this table for funds. So one more time. Oh, here we go. Oh, we're populating the table. Oh, look at it go. Oh, we're populating the table, finding those potential gears. You can see it's reading. It's reading the table as well. It's our writes and our reads. So the blue ones. This is me reading the table, checking for locations, checking again to see if I've seen this gear before, right? And this is something where, right, I'm starting from the start all the time, and I could probably have moved the start down further as I found gears, because once you find a gear, you can only really go back so far to be able to find another gear, sort of thing, right? You only really travel behind so far. So here we go, still going through. Oh no, we got to the end. So my table ends up being, we get to 6830. So what is it? We are under 1 kilobyte, I think. What is it? No, we're just over 1 kilobyte, I think. What is it? Wait, it's 50 is a... Man, I can't do the math in my head right now. I know what I can do. I can just select all of this and it'll tell me how many bytes it is. Yay, here we go. I went too far. Where are we? There we go. There we go. 2099 bytes I use. So just over, well, just over 2 kilobytes. Just over 2 kilobytes of memory to make this table, which is not the most efficient. Wasn't the most efficient. I could have, like I said, once you travel like so far down, I think effectively, once you've gone past the trailing byte, or past the leading byte, whatever you want to say, you're probably not going to be finding a gear. But yeah. Yeah, you shouldn't, like, if you find a number that's next to an asterisk, the trailing asterisks, right? The trailing the asterisks in the table couldn't be much further than a trailing gear behind, sort of thing. I don't know. I'm getting confused a bit, I think. But yeah, I should have been able to start cutting back the table or rotating the table a certain amount, so that I could use a smaller memory area and reduce the search time. But it really, I mean, you look at how much time is spent counting up part 2, doing the multiplication. The big time factor was that loop that was doing the addition there. That was the big time factor. Not so much the checking the table. I think that probably took basically no time at all. Each loop, each instance. Yeah. Anyway, so that was day 3. The code, how much code did this one take? Let's see. Our solution here, what do I do? Clocked in at like 611 lines of assembly, which is the longest so far, but is not the longest day that I completed. So we've got something else to look forward to. And this video is now, it's over an hour long. So we'll end it there. I hope you join me for day 4. I think day 4 will be interesting as well. And I hope you enjoy it. Catch you again.